I want a little bit talk about vortices and in vertical shear instability in global models, and it's work done by me in cooperation with my supervisor Hubert Klar and other members of the MPIA and from Tübingen. And yeah, so in general, vortices are somewhat an everywhere feature we have both in atmospheres, for example, as hurricanes on Earth or as the Great Red Spot on Jupiter, but also we find them more and more in protoplanetary disk observations, for example, in Ophiuchus Iris 48. And we have already heard a lot about it, but again, we have vortices are particle traps, and basically vortices can be put into two categories. We have cyclones and we have anticyclones. The primary differences in how the pressure gradient is pointing in the vortex. So when you have an anticyclone, the pressure is highest in the center of the vortex, whereas for a cyclone, it's lowest in the center and the gradient increases outward, which means that we can rule out having cyclones as pressure traps because they will always expel particles, whereas anticyclones will naturally concentrate the particles in the center because the particles will drift to where the pressure is highest. So from stabilities, we've already read a lot about it. So I put up a little zoo of turbulence mechanisms we have in planet-forming disks. So beginning with MRI, which was kind of the poster child for a long time, and after we had non-ideal MHD effects, then we got a lot of the hydro instabilities over here. So the vertical shear instability, which I work with, but also will show some convective overstability results, and we also have the zombie vortex instability and also vertical convective instability, which can theoretically happen in disks. So for what will also be relevant later is the Rossby wave instability, and but we also know that turbulence is kind of the only trigger for, especially for vortices through the Rossby wave instability, especially for we have non-ideal MRI effects, and then the edge of the dead zone is also a region where we can trigger the Rossby wave instability. So a bit on the VSI in general. So the VSI operates only in disks which are baroclinic, which basically means that the pressure is dependent not only on density but also on temperature. In our models, we realize this by having a density gradient in the disk, which has is proportional to R to the power of P, and a temperature that is proportional to R to the power of Q, and the what makes the disk baroclinic is that Q is not zero. And then the disk has radial and vertical shear, which is shown by the impression for V phi, which then gets this critical term here, which depends also on the height and not on the radial distance. And then we can show that the form of omega is then a parabola here, and whereas for q equals 0, this would be a straight line and would have the disk rotate on the cylinder. And then I also show here where the gradients of omega for the angular momentum and the angular kinetic energy go. So angular kinetic energy and orbital frequency increase inward, whereas angular momentum increases outward in the disk, which is technically, if we wouldn't have vertical shear, would be a problem because then kappa z here would be 0, and we would basically recover Reynolds stability criterion, which would make the disk unconditionally stable, which is kind of what we not want. So then, because we have now this kappa z unequal 0, here with the vertical shear, we can then have the situation that if our particle moves slightly upward, it has also to move slightly outward to follow the surface of constant angular momentum. And if it does that, it comes into a region where the disk has a lower angular kinetic energy than the particle itself. So the particle has a higher kinetic energy. So if we now have the particle not be pushed down due to buoyancy in the disk, which we can achieve through efficient cooling, the particle will not be stopped from using this kinetic energy to move upwards further, which then creates the instability. So previous work on VSI has largely been either in 2D axisymmetric models or in 3D, I call them cake piece models, which usually means that to get a very high resolution per scale height in the disk, you sacrifice part of your of the global model of the disk. So you just choose maybe the azimuthal direction to be 45 degrees or so to get really a good resolution, but then you don't get the whole model. And what I was investigating is if this gives us, this takes some structure away from the models. So, and here, I say that we start with 45 degrees and then we double the azimuthal extent of the disk. And then we find that if we go go beyond 180 degrees, so more than half the disk, we actually find that we get not only small scale structure, but we get large scale vortices in the disk, which then also stay for longer time, which we can see here. So we have that vortex, and which corresponds to the outer vortex in all simulations, snapshots I show. So what I now use was, here was P is minus 0.66 and Q is minus 1, which is not the ideal setup for what we would expect in the protofinite disk, but it's actually a setup that is primed for comparisons with the convective overstability, which I will talk about later. So we also looked into what happens to the Reynolds stresses via the alpha value from Shigora-Sonyaev. And we then find that in the initial stage, it's about the same, but then when we go to the saturated values at the end of the simulation, we see that for the 45-degree disk, that alpha is higher in the end than for the 360-degree disk. So we may have, so we have low values for alpha for a global model, which means that when we compare small azimuth disk simulations, we may have missed something before. So, and we then also looked at the vortices specifically, and we were interested if the vortices are extended through the whole disk or not. And we find actually that the vortices have a coherent structure, can be seen here, which is the same at z as 0.5 scale heights and at 1 scale heights. But if we go to 2 scale heights up in the disk, we see that the vortex starts to rejoin the background flow and disappears. So there seems to be a finite height, and also the vortex has kind of the finite size of about 1.5 radial scale heights. So the disk automatically caps it before the vortex goes supersonic at the boundaries. So, and to really see that the vortex exists over the whole time and is not a transient feature, we used an algorithm to smooth out the high frequency turbulence in the disk, and then looked for the minimum in vorticity, which is so the bluer the plot, the the smaller is the minimum in vorticity, which constitutes a vortex. And we see that for our simulations that did show a vortex, that those vortices are very long-lived and also start to migrate inward at a slow rate. So, and we also see that some vortices actually start to merge once they merge, so they migrate too close to each other. So, and building upon that, that was only for one specific set of parameters, but we had chosen h equals the aspect ratio of the disk equals 0.1, which is rather large for a typical disk. So we looked if this would also happen if we choose a lower aspect ratio, and which we did here. So we chose 4 different aspect ratios of between 0.1 and 0.03. And we see that the vortex formation happens for all of those parameters. But we also see that the strength of the vortices decreases with decreasing scale height. And we also see that the disk becomes somewhat more ordered when we go to the lowest h. But that they exist per se is, it seems to be an ubiquitous feature. So going to net instability, as I said, VSI is not the only instability in town. And this is a result from simulations that are performed by Hubert Klar, which show the convective overstability. We have here a small part of the disk, which is set at Z0.5 h above the midplane, so we're not going into them, so go out of the midplane to look at the disk. And I'm going to play that. We see first that we have kind of this vertical modes, which we think are from the VSI, and then but they don't grow. And then we see inside those vertical modes, we see the radial modes of the convective overstability start to form small vortex-like structures. And this is temperature, so they then start to interact and start to grow bigger and bigger. And I don't think I show the whole thing, but eventually this will be one convective cell over the whole box. But we also see that we are already at over 1,000 orbital times, so the growth times are very, very long of this instability. So, and I think we had this form of that diagram for also kind of often today. But going over it again, this is work from a bachelor student in our group, and he used the 1+1D model of the disk to calculate self-consistently at which parts in the disk certain instabilities can form. So we have the VSI in green here, so which preferentially can grow outside of a few AUs and also inside of one AU where we have actually a vertical convective instability possible. And so we can have actually vertical convection, which also means that the VSI can technically be active. And the convective overstability, which goes a little bit farther in and then usually can form preferentially outside of the midplane, farther out in the disk and also inside disk. And the gray region here is where the subcritical baroclinic instability can amplify vortices that have formed in the disk over a large range. So, but up to now, we kind of didn't just vorticity, But vorticity is not something we can actually observe in the disk. But we also cannot observe the gas of the disk, so we have to go to the dust. The simulations I showed you were without any dust modeling, but to just see if the vortices we found are actually visible, we used a steady state dust distribution model from Lyra and Lin to model what the dust would, the steady state concentration would look like, and then used RedMC 3D to calculate the intensity, and which I now fold with a small beam to make it more comparable with observations. And we actually find that when we choose for the sigma 0, which is the reference density we scale our gas disk with, to about 16 grams per square centimeter, we actually recover a disk which looks very much like current disk observations, example of MWC's 758. And we also looked at smaller ones where then we also don't resolve one of the vortices anymore, and where the vortex becomes really bright against the disk, which is usually not what is observed. And for this disks, we see that the vortex extends more as is expected because the Stokes number is lower at higher gas surface densities. But at this point, for the largest model, the disk actually would be gravitationally unstable. So this may not, then VSI may not be the dominant mode anymore. So to conclude this, hydrodynamic instabilities exist over large portions of the disk, barring MHD effects. And we find that the VSI has large vortices seated in the disk, which are also very long-lived and extend over about 2 scale heights. And we think that the VSI can also explain some of the observations which show multiple asymmetries. Thank you.
Questions? Vlad?
So I got a question from Orkan here. Apparently he wants to ask, but he cannot talk on the mic. He's asking if the vortices are intermittent or not?
You mean that if they...
Intermittent, yeah.
No, they're actually, they're not intermittent, they're static features, so they once they appear, so some vortices may interact with each other and then may become weaker or harder to detect, but they don't completely disappear.
Can I ask a question myself? So first, what is VCI? In the Butcher diagram that you showed, you had
it's instability through vertical convection, so the entropy gradient becomes negative.
So that's the same as the convective overstability, but in Z, right?
Vertical entropy gradient.
Right. Okay. Is that what showed there? I mean,
yeah, I can.
The video that you had, that one there.
No, that is convective.
Overstability, but that's in Z, right?
Yeah, there's convective overstability. It's R and Z, but I think this is only a slice of the whole simulation. So this should also have at least some Z, some theta in there. So, but if I go back to the beginning, so the VCI is basically that. This here becomes negative, so because this is the stability criterion, then if this is negative, the whole term is negative, and the disk will be unstable. So this is basically VCI.
Jeremy?
Just wanted a clarification. You didn't say anything about I didn't hear you say anything about the vertical temperature structure. I mean, realistic models of disks in radiative equilibrium are are warmer as one goes away from the midplane, typically, because the upper layers are exposed to the radiation.
This model is...
That can make them baroclinic, but what did you assume? Vertical?
I assume very rapid cooling, so the disk is nearly vertically isothermal.
Vertically isothermal. Okay. If I could be permitted a second short question. When your vortices merge, what happens to their sizes? Do they get broader, or are they still limited by this 1.5 scale height?
I didn't look specifically into that, but I don't recall. I don't think they become bigger than this 1.5. But it's difficult because when they start to merge, before they really merge, there's a period where they interact and they in vorticity, then they shear each other out a little before the merging happens. So it's hard to see, but I can look into it.
There are some observations that suggest that the vertical diffusivity should be less than corresponding to an alpha of 10 to the minus 4. And I was wondering if the vertical shear instability being so anisotropic, if that doesn't cause more vertical mixing than is observed. Did you look into that?
I didn't look specifically into that because it's hard to calculate the vertical stresses in particular. But I know that in this one paper, Mario Flock looked into that, and they show that with their simulations, we have much lower angular momentum transport in radial direction. That they find that some disks are explainable with VSI at when you compare the the vertical turbulent speeds, but some are not.
Any other questions? If not, let's go ahead and thank Natascha again.